Hello, everyone. Welcome back to my lessons. Today we decided to continue solving paper 2 for IBHL students. Remember last time we started the practice this paper. We stopped with Liouville structures. Okay, let me check. Is it working? Yes, it does. Okay, so now I mute myself. Right. So we discussed that we will continue solving IBHL paper 2. SL students can also join because I will tell you which questions you don't need. Also, if you're an A-level student and working at a B or lower grade, then you can also benefit from the questions. Right. So I don't know how much time we need for that to finish the paper because we're only on question 3 out of like, what is it, 9 or 10. But I thought we need 2 lessons. But now the heat wave is over in England. The rain is back, so I'm in my work mood. Maybe we'll have time to finish, but I don't promise. Let's see. We'll just start. Yes, and by the way, I also scheduled a lot of lessons for this week. So tomorrow, I think it's tomorrow. Tomorrow we'll do A-level organic mechanisms, and also for Friday I scheduled the entire IB structure 1.1, 1.3 for IB students. So if you want to get notifications about the lessons, you can subscribe to my channel, and then you will get the notifications. And also, if you have friends who are studying chemistry, IB or A level, you can tell them. All right. So let's start. Let's continue. So we were doing this paper. The link was below. Yeah, from Save My Exams. We stopped at this question, question 3a. We wrote some Liouville structures. Next question. A crystalline ionic compounds. Uh, yes, I'm still live. Crystalline ionic compounds do not conduct electricity. State and explain in which states ionic compounds conduct electricity. Okay, 2 marks. Whenever you're asked to explain either melting or boiling point or electrical conductivity, what do? We always state the structure, right? So we say that they have a giant ionic lattice. Yeah, do we need to say that? State and explain. Actually, not here. It's for the next question. Yeah, just state and explain in which states. Yes, so in which states? So there are ions, right, in the lattice, and when ions are immobile, as in a solid, then ions cannot move, so no conductivity. When ions can move, then substance conducts electricity. So to conduct electricity, you need mobile charged particles, which could be either ions or delocalized electrons, as in metals or graphite. So it would be then a molten. Yeah, so I'm choosing the states when ions are mobile. So molten state or aqueous state. And yes, so ions are free to move and carry charge. To move and I was hesitant whether I should say something about ionic lattice, and I realized that I don't have to say because you see it's in question C, they ask to explain melting point, so probably I don't have to say it here. So it's very unlikely that you would have to give the same answer for both. Yeah, question for both sub questions. But if you said that it has a giant ionic lattice, it would be safer, so nothing wrong with that. Just if you add anything extra to your open response questions, make sure that you don't have any contradictions. Yeah. So here it would be fine to mention, but I have to say it in the next question anyways. Um, yes, all good. The melting point of sodium chloride is that very high. Explain with reference to structure and bonding why sodium chloride melts at such a high temperature. You see, with reference to structure and bonding. What is the bonding? So it's a metal and a non-metal, so it's an ionic bonding. Since it's an ionic bonding, it has a giant ionic lattice, no other option here. So giant ionic lattice, it's 3 marks by the way. Yeah, so okay. Has a giant ionic lattice. So this is probably your first mark. Then we have to refer to the attraction. Yeah, so what attraction are we breaking when we're melting? For ionic substances, when you melt or boil them, you always break ionic bonds. So we say, so it's a giant ionic lattice with strong electrostatic forces of attraction Between what? Well, for ionic bonds, you need to know that it's between the oppositely charged ions, right? And for IB, if you just say oppositely charged ions, that's fine. If you're unsure, because if you say between Na plus and Cl minus, it's fine, but you have to make sure that you put the charges on the ions correctly. So if you're unsure, just say between oppositely charged ions. That's your second mark. And the third mark is always, so a lot of energy is required to overcome that attraction. Right. So in these questions about melting and boiling point, so if you see it's a low melting point, you can always get the mark by saying, so low heat is needed. Yeah, if it's high melting point, you say high, large amount of heat is needed. So, well, large, not amount, a lot of heat. Let's say a lot of heat is needed. Yeah, you cannot say amount of heat. A lot of heat energy is needed to overcome the attraction. So let's sum up. If you're melting ionic substance, you're always breaking electrostatic forces of attraction between oppositely charged ions. If you're melting or boiling simple molecular compounds, a simple covalent, you're breaking intermolecular forces which are weak. If you're melting giant covalent, you're breaking strong covalent bonds. Silicon, graphite, yeah. And so you're breaking electrostatic attraction between the shared pair of electrons and nuclei. And if you're melting or boiling a metal, then you're breaking metallic bonding, which is attraction between the lattice of positive ions and the sea of delocalized electrons, right? Right. Okay. Next question. We can use electronegativity values to deduce whether a compound is likely to be ionic or covalent. Yes, we can. Use section 9 of the data booklet to state and explain whether each of the following compounds are ionic or covalent. So yeah, we can judge, we can discuss, like we can decide what bonding the substance has based on the difference in electronegativity. So the general rule is that if electronegativity difference is higher than like 1.8, in different books you'd have a different value, but approximately that is what's working. Yeah, so if it's electronegativity difference is more than 1.8, then it's an ionic substance. If it's less, then it's covalent, polar, or nonpolar. Well, let's see, ICl. So I have to find the electronegativity difference between iodine and chlorine. So that's my data booklet, table 9. That's electronegativity value, so the bottom one. Right, so chlorine is 3.2, iodine is 2.7. So 3.2 minus 2.7, which is what, 0.5, right? 0.5 is covalent bonding because it's less than 1.8. And then strontium chloride, that's RCl2. Well, Cl is 3.2 and strontium is 1. So minus 1, which is 2.2. That's pretty ionic, yeah, above 1.8. RBI. Okay, rubidium is 0.8, iodine 2.7. So 2.7 minus 0.8. Was it 0.8? Let's see. Yeah, 0.8 for rubidium. Oh my gosh, this is 1.9, or is it 2.7 minus 0. Yes, 1.9. That's ionic as well. And Hi, so I we said is 2.7, hydrogen is 2.2. 2.7 minus 2.2, it's 0.5, so covalent. Covalent, yeah, both are polar covalent because its electronegativity difference isn't 0. Okay, yes, let's see, next question. Phosphine pH3 is a gas formed by heating phosphorus acid H3PO3 in the absence of air as shown in the equation below. 3.45 times 10 to negative 2 moles of H3PO3 is completely decomposed by this reaction. State the expected molecular shape and expected bond angle of pH3. Okay, we did it last time. I'll remind you how we identified the shapes. So to identify the shapes, what did we do? We drew a Lewis structure first. Yes. To find out the Lewis structure, we need to find the number of valence electrons in the pH3 molecule. So phosphorus. let's go to the to the periodic table. Phosphorus is in group 15. There it is. So it has 5 electrons in the outer shell. Hydrogen, group 1, so 1 electron. So, okay, let me see, can you see it like that? Yeah. Okay, so pH3, it has 5 electrons from phosphorus. 3 times 1 is 8. So it has 8 electrons in the outer shell in total, which means that it's 4 pairs. So then you put the central atom in the center, so P is in the center. Connect side atoms with single bonds. Then the next step would be to assign octets to the side atom, but hydrogen is an exception because it can only have 2 electrons in the outer shell. So that's why hydrogen stays like that. And then I count how many pairs out of 4 I have used up. So I have used up 1, 2, 3. 3 out of 4, which means that the 4th pair is the lone pair on phosphorus. And I don't have a table today, but I hope you remember that if you have 3 atoms bonded to the central atom and 1 lone pair, that gives you a trigonal pyramidal shape. Trigonal pyramidal. And the bond angle is 107. Do we need the bond angle? Yes, 107 degrees. Okay, that you will memorize before the exam. Right. If you're unsure how we did it, just check my previous lesson on the same paper. I explained this in detail, so you'll understand it from there. Right. Next, calculate the volume of phosphine gas formed in cubic centimeters at 100 kilopascals pressure and 210 Celsius. The volume of phosphine gas were, well, apparently in this reaction, right? So what do we know? We know that we had that amount of moles of acid. So it's 3. It's so annoying when they put 10 to the negative 2 when they could have just said 0.0345. So, okay, so we have that amount of moles of acid, and we need to find the volume of phosphine. So what I can do is I can apply molar ratio of H3PO3 and pH3, right? Because I have a balanced equation. I have moles of one of the substance, so I can find the moles of everything else. So let's find the moles of pH3. Moles of pH3. So the ratio is 4 to 1. So I would take this number and divide it by 4. 10 to the negative 2 divided by 4, which is 8.63 times 10 to the negative 3 moles. That's moles of phosphine. Then we don't need anything else from the... Oh, my video is blocking the text. All right, then what do we do next? So now we know the moles of the gas. Right, and we need to calculate the volume of this gas. Obviously, we cannot use the standard conditions because 210 Celsius, it's not standard. That's why I will have to use ideal gas expression, so PV equals to nRT. nRT, and from there I will rearrange it to find the volume. nRT over P. And in these questions, remember the units. For A-level, if your guys an A-level chemistry student, your units are temperature in kelvins for everyone. Volume must be in cubic meters. Pressure must be, volume in cubic meters, pressure in pascals, right? So you could use pascals together with cubic meters. If you're A-level, that's the only units you could use. If you're doing IB, you can do these units, or you could also do kilopascals and cubic decimeters. You'd get the same answer, and you're not marked off as far as I know at the time of recording this video, okay, doing this live stream. So safer to use these units, yeah. But so as of today, you're not marked off in IB as well. Right. Well, I will use IB units just, to make it faster. So, all right. So moles, 8.63 times 10 to the negative 3. R, it's 8.31. That's in the data booklet. It's a gas constant. Temperature must be in Kelvin, so it's 210 Celsius. So 210 plus 273 to convert it to Kelvin. So that's 483 kelvins, and divided by pressure. I'll keep it in kilopascals, and then I would get cubic decimeters. Right, now I just calculate -3831483 over 100. That is 0.346. 346 cubic decimeter, because again, pascals, cubic decimeters, and we need it in centimeters. Is it a 5-mark question? That is so weird. I doubt that's 5 marks, to be honest, but well, if it's 5, good for you. So to convert from decimeters to centimeters cubed, I have to multiply by 8,000. Done. Okay, next. 1.85 grams of white phosphorus are used to make phosphine according to the equation. We have another equation. This phosphorus was reacted with 75 cubic centimeters of 4.5 molar sodium hydroxide solution. Did you show in your working which was the limiting reagent? Oops, sorry. Yes. Right, what is the limiting reagent? What is... I'm still alive, right? Just double checking. What is the... Where's sodium hydroxide? There it is. Yeah, it's just written as an ionic form. So sodium hydroxide is NaOH. So for every NaOH, you get one OH minus. To find the limiting reagent, what do? We need to convert both reactants in moles. I mean, there are 3 reactants. There is also water, but obviously it's aqueous solution, so water is in excess. It's everything happens in water solution, so in aqueous solution, so water is definitely in excess. So we're choosing between P4 and OH minus. So first I'll find the moles of P4. I have the mass given 185, so I'll do mass over MR. That's a 5. What is MR? Okay, let's go to the data booklet and find phosphorus is 30.97 times 4. Times 4, that's MR, right? So 4 times a relative atomic mass. 97 times 4, which is 0.0149 moles, and then I find the moles of sodium hydroxide. Because NaOH produces one OH minus, I can just say that it's the same as moles of NaOH. And I do, okay, so I'm given concentration and volume, so the formula to find the moles from there is C times V. Concentration times volume in cubic decimeters, so 75 over 1,000. 0.075, which is 0.0, not 0, 3375, so 8 moles. All right, I found both. Yeah, I found both moles of P4 and OH minus. What do we do next? Next to it, well, limiting reagent, what is it? Limiting reagent, it's the one that's fully reacted, and the other one would be in excess. I just have to check which one would be left over, which one would react completely. You can start from any reagent and apply the molar ratio. So I will like think about it this way. So if I have 0.0149 moles of P4, how many moles of OH minus would I need to react with this amount of P4? Well, 3 times more, right? Because it's in 1:3 ratio. I will write it as a sentence. You don't have to, but I will, just to make it clear. So I would say that for 0.0149 moles of P4, we need, I'll say we need, that's okay, 3 times 0.0149, that would be the moles of OH minus. So 0.0447 moles. So that's how many moles of OH minus you need to react with all of the P4. And how many moles of OH minus, yeah. And how many moles of OH minus do we have? Well, we have 0.338. That's more than what we need. Yeah. So I say 0.338 is more than 0.0447. What does it mean? It means that OH minus will be in excess, so I will have some OH minus left. And it means that P4 is the limiting reactant. and the OH minus is in excess. You could have started with OH minus. You could have said, okay, if we had 0.338 moles of OH minus, how many moles of P4 would we need? Well, it's 0.338 divided by 3, right? Again, I'm applying the ratio, and that would be around 0.1. And 0.1 is much more, 10 times more than what we have. Yeah, so P4, we don't have enough of P4 to react with the entire amount of OH minus. I hope that makes sense. That is how many marks? Well, usually it is 1 mark actually. And usually, as long as you find the moles and come up with the correct answer, that's enough. Right, next question. Let's see, next question is, using section 2 of the data booklet, determine the volume of phosphine pH 3. Measured in cubic centimeters at standard temperature and pressure that was produced. Give your answer to 3 significant figures. Now this is at STP, and the data booklet would give you the volume of STP at STP, so it would say that molar volume is 22.7 cubic decimeter per mole. Let's actually check, is it 22.7? I think it should be 22.7. Yeah, cubic decimeter per mole. That's the volume of gas, of any gas, ideal gas, at standard conditions, which is 273 kelvins and 100 kilopascals pressure. Yeah, that's not the same standard conditions as, for example, used for enthalpy. There it's 298 Kelvin, so be careful with that. Right, 22.7. So we need to find the volume of phosphine in that reaction. So we need to find the moles first. Moles of pH3. So what do we know? We know that P4 is the limiting reactant, right? We just established that. And remember that the amount of product, the number of moles of products, can only be determined from the moles of the limiting reactant, which is very logical because P4 has reacted fully, OH minus hasn't fully reacted, so you cannot find out the moles of products using OH minus because not all of it reacted. So I'll use the ratio of pH3 to P4. It's 1-to-1 ratio, which means that the moles of pH3 would be the same as P4, so 0.0149. 0.0149, and then I use the molar volume to find the volume. It's N times 22.7 Okay, 0.0149 times 22.7, which is 0.338. And because the units are a cubic decimeters per mole, that's from the data booklet, very handy to check the units out. So we get decimeters cubed. And we need it in centimeters, so again, I multiply by 1,000 to convert from decimeters to centimeters. cm cubed, that's your answer. Right, that's fine. Next question. Question 5. This question looks at how entropy change of water varies with temperature. Okay, so we have a graph. This is, I think these questions would be very typical for the new spec. Yeah, so just keep an eye on those. So we have entropy change, and temperature, right? So what happens is that we're kind of heating the substance and see how entropy is changing. So what happens here? So when you go from 0 to some Kelvin, so you start with a solid, right? So at this point you're heating solid. Yeah, so this part of the graph is heating solid. Then here, when entropy is increasing but temperature doesn't change, it's the phase change. So you go from solid to liquid, then you're heating liquid here, then again another phase change. So the vertical lines are the phase changes. This would be going from liquid to a gas, and then you're heating gas, entropy again increases. Okay, let's see what the question asks. The entropy of water is 0 when the temperature is 0 kelvins. Kelvin, explain why with reference to the water molecules in your answer. Well, at 0 kelvins, this is the temperature that in practice we cannot achieve, but theoretically speaking, at 0 kelvins, particles are not moving. If they don't move, then it's there is zero disorder, because remember, entropy is the measure of disorder. The more disordered the system is, the higher the entropy. So at 0 kelvins, particles are not moving, so the perfect, everything is in perfect order. And that's 2 marks. Yeah, so I say at 0 kelvins, particles of or molecules of water do not move. So no disorder. No disorder means that entropy is 0. Next question. Explain why the entropy change delta S is larger at temperature T2 than temperature T1. So they ask why this entropy change is larger than this. Well, let's see what happens here. So at temperature 1 we have a phase change from solid to liquid, and at temperature 2 we have a phase change that is from liquid to gas. And then think about the increase in disorder, right? When you go from solid to liquid, does disorder increase? Well, yes, because in solid, particles are moving, like vibrating about fixed positions. In liquid, particles can slide over each other, so that increases the disorder. But when you go to gas, that's chaotic, right? The gases move randomly at high speeds and so on. So the increase in disorder when you go from solid to liquid is smaller than the increase in disorder when you're going from liquid to gas. That's why the increase at T2 is higher. And that's 2 marks, right? So you have to show that you understand that the entropy change is due to the phase change, and that's what I will write. Yeah, so let's see. I will say at T1 solid goes to liquid, which is melting, right? At T1 solid goes to liquid, and at T2 liquid goes to gas. The increase in disorder, well, we can say gases are the most disordered, so the increase in disorder at T2 is greater. I would say gases are the most disordered. And the increase in disorder when going from liquid to gas is higher than when going from solid to liquid. Yeah, that's why we have a higher entropy change. Okay, next question. Standard entropies can be used to calculate the entropy change of a reaction. Delta S, for example, for the formation of nitrogen monoxide from... Oh yeah, guys, I forgot to mention that this is the only question that is needed for HL students, right? So IBSL, you don't need this question, entropy question. Everything else was SL. Yeah, everything else was SL. This one is HL. Right, so we have a reaction and we're given entropies. Use the data given to calculate the entropy change for the reaction between nitric oxide and ozone. Okay, I'll just copy this so that I can see the reaction. Right. So that's the reaction for which we need to find entropy change. The formula for entropy change, it's delta S equals to S of products minus S of reactants. That's reactants. Okay, so delta S. Entropy of products. What are the products? These guys. So entropy of NO2, 240, plus entropy of O2, 205.2, minus all the reactants. NO is the reactant, and O3 is the reactant. Remember, if you had coefficients, you'd have to multiply, by the coefficients. So, for example, if you had 2O2 here, I'd do 2 times 205, So coefficients are taken into account. And what else? Yes, and also remember that entropy values for elements are not zeros, right? Everyone's confusing this with enthalpy change of formation. So enthalpy change of formation, for example, for oxygen element in standard state would have been zero, but this is not enthalpy, it's entropy. Yeah, so don't confuse these two. Well, right, and now I just have to calculate 240 plus 205.2 minus that and minus 238.9. It's negative 4.5, and the units for entropy, you don't get any marks for units, but just in case, joules per Kelvin per mole. Remember the kelvins are there. And it's joules, right? Not kilojoules. Next question. Okay, the contact process is a method used industrially to form sulfur trioxide by reacting sulfur dioxide and oxygen. So we have this reaction, and the equation is given a substance, and we're given formation enthalpies, delta HF. Yeah, now you see there is no oxygen because yes, for oxygen enthalpy change of formation is zero because it's an element in its standard state. Let's see, what do we need to find? We need to calculate the standard enthalpy change of the contact process using the data provided. Please do not draw any Hess cycles. 2 marks, just use the formula. The formula is, by the way, in the data booklet now. There it is. Yeah. This is also HL. Um, now, so delta H, it's delta H of products minus sum of delta H of reactants. We just use that, no Hess cycles. For A level, you can also use this formula. No one forces you to draw any cycles. Even if they ask you to draw the cycle, you only lose 1 mark if you calculate everything correctly, but without the cycle. So this is more straightforward. Okay, I'll put it. Why is this formatted so badly? Well, okay, you know what? I'll fit it in here. I hope you can see it. So I will say, I hope you're not watching from the phone. I'll write the equation here. So delta H of reaction, it's delta HF of products minus reactants, yeah? Well, let's see. So products minus reactants. So I have two products, 2SO3 minus delta H of reactants. Oxygen is zero, right? That's an element. And then 2 times negative 297 product minus reactants. Okay, so negative 2 times 395 plus 2 times 297, which is negative 196 kilojoules per mole. Right. The standard entropy change of this reaction is negative 189 joules per Kelvin per mole. See that, joules, right? Use this value and your enthalpy value from part 1 to calculate a value for the free energy change of the reaction at 298 kelvins. What is free energy change? It's Gibbs free energy delta G, which has a lot of formulas. We need this one because it's the one that uses delta H and delta S. That's the one that I'll be using, so I'll put it here. So delta G for the reaction. It's delta H minus T delta S. What do we know? We just calculated delta H, yeah? Delta H was, because they say use your answer from part 1, yeah, that. So we calculated it's minus 196 kilojoules per mole. Delta S, they tell us what it is. It's negative 189 joules per Kelvin per mole. And we need to find delta G. So, well, guess what's the number one mistake in these questions? Obviously the units, right? So you have to have delta H and delta S in the same units. Usually those units are kilojoules because usually they would ask you to find delta G in kilojoules. Here they don't say which units you use, but normally it's kilojoules. Or if you do joules, that's fine for this question, but just remember to use the same unit. So minus 196, I'll do it in kilojoules. That's my delta H. Yeah. Minus temperature in kelvins, they say it must be 298 kelvins times delta S. That's my delta S. I'm converting it to kilojoules, so it's negative 189 over 8,000. Let's see what that is. So negative 196 times, no, plus 298 times 0.189, which is negative 140. Do we need significant figures? Well, to three significant, I'd say, yeah. So minus the negative 140 kilojoules per mole. Done. Yeah, we answered this question too. And then use your answer to part 2 to explain whether the reaction is feasible at 298 kelvins. The easiest question of all time. If delta G is negative, it means that a reaction is feasible. So that's what you just say. You just say delta G is less than 0, so feasible reaction. That's it. Next. The value for the free energy change is an indication whether the forward or backward reaction is favored. The curve that we would expect to see for the reaction between sulfur dioxide and oxygen is below. Explain why the curve for this reaction is shifted to the right hand side. That's the curve. Okay, so explain why the curve is shifted to the right hand side. Well, what does it say? So this graph, it's also, I think it's a new one and a new specification. Maybe it was there. I don't remember if it was there before. I did teach it, but I feel like it was a little extra. But what does this graph show? So it shows how Gibbs free energy changes when the system reaches equilibrium. So you see, if you have only pure reactants, Gibbs free energy is high. But when you start forming products, Gibbs free energy decreases, and at some point it reaches the minimum, right? So Gibbs free energy reaches the minimum, and that's your equilibrium point. If you form more products, you see, you have to, delta G becomes positive, so you see, you have to increase Gibbs free energy. That's why you don't have, like, that's why you can see that this reaction is reversible, first of all, and you can see that at equilibrium you have more products than reactants. That's what we have to say. Yeah, so because if, for example, we had more reactants than products, well, then it would look like this. Yeah, so you would see the minimum closer to the reactant side. We see that equilibrium is reached closer to pure products, which means that what do we need to answer? Yeah, so we just say that equilibrium lies towards the reactants, to the right. So reactants are favored. And that is 2 marks. Yeah, so let's say that. So we say that when delta G is negative, reaction is feasible. Yeah, so you see it's delta G is negative here. So when delta G is negative, reaction is feasible, and the equilibrium point is closer to the product. Let's say equilibrium is closer to the products, which means that the reaction mixture contains, the equilibrium mixture contains more products than reactants. More products than reactants, which means that the products are favored, right? So the right hand side is favored. Or forward reaction is favored, something like that. Yes, forward reaction is favored, or right hand side reaction is favored, or yeah, forward or right hand side, or products. Yes, okay. Next question. Oh, how many do we have? So 6, 7. Oh, let's see how long is this stream? 39 minutes. Okay, well, at least 20 minutes we can do. Right, question 6. A Maxwell, in any chemical reaction, the particles will all be moving around a different, okay, that's just, let's see. So we have a Maxwell-Boltzmann distribution. Yeah, what does it show? The Maxwell-Boltzmann distribution is a graph that shows the distribution of energy amongst particles within a chemical reaction. Okay, a label x and y axis on the graph. So the x-axis is kinetic energy, the y-axis would be a number of particles or a fraction of particles. So like, how does it work? Imagine if you had like a vessel with gas. There are millions and billions of molecules, right? And if you were able to measure energy, kinetic energy of every single molecule and plot it on the graph, so here you would say fraction or number of molecules, particles maybe, just in case, yeah, particles. So if you were to measure the kinetic energy of every single particle, and you would say that, okay, for example, 200 particles have this energy, then 300 particles have that energy, and so on. Yeah, so you, because there's so many particles, you would have a continuous graph. Yeah, because there are so many molecules would always almost look continuous. And when you draw it out, I'm now marking a level, and I have to mark the shape of this graph. So what do we look at? So we look at the starting point. It must be at 0. And we looked at this final part. It does not intercept the x-axis, and that this final part, it's not too flat. So like, if it's going like this for too long, you also lose a mark. Yeah, just in case. I'm telling you this now. Okay, then label x and y. We labeled sketch a distribution for the same sample of gas at a high temperature. Label it as T2. Well, let's do that. So again, it starts at 0 because no molecules have 0 energy, right? So 0. And then the peak shifts to the left. Oh, that's an ugly one. The peak shifts to the left and becomes lower, and this tail of the graph, it is above the tail at a lower temperature. If you don't label T2, you can lose a mark because they say label T2. Right, what's happening at high temperature? So what's happening at a high temperature? You are shifting molecules towards higher energies, right? So you had, at lower temperature, you have a lot of molecules with this low energy, right? Now at T2 you have much less molecules. That's how many molecules you have with this low energy. But then as you go to higher energies, for example, this is a high energy, right? So you have few molecules with that high energy at low temperature, but you have more molecules with that high energy at a high temperature. I hope that makes sense. So labeled, sketch the distribution as sketched. Next, state why a Maxwell-Boltzmann distribution curve always starts at the origin and what the area under the curve represents. So that actually we already mentioned. So it starts at the origin because there are no particles with 0 energy. Starts at origin. There are no particles with 0 energy. And what does the area under the curve represent? The area under the curve represents the number of molecules in the vessel, right, in the reaction. So remember also, sometimes you'd be asked to write down the activation energy. So activation energy would be somewhere here. Yeah, activation energy. And so, for example, the area under the curve, this area that is higher than activation energy. So this area that I shaded, this is the number of molecules that have energy higher or equal than activation energy. So these are the molecules that can react. But the total area under the curve, it shows you the total number of molecules in the vessel. And strictly speaking, the total area under the black curve must be the same as under the red curve because I didn't change the number of molecules. No one will check. Yeah, I don't know, mine doesn't look really similar, but no one will check that obviously, but it should be the same. Yes. What did we say so far? Yes, did we answer that? What the yes, okay, so the area under the curve. The curve shows the number of particles in the reaction. Or equals, yes, so if you just really calculate the area, you'll be able to, by integration or something, you'll find the number of molecules. Shows the number of molecules in a reaction. Yes, next question. Chemical reactions take place at different speeds. Particles must collide with each other in the correct orientation and with sufficient energy. Explain why most collisions between particles in the gas phase do not result in reaction taking place. Well, yes, that's true, because only particles that have enough energy to react and are in the correct geometric orientation would react. So now, um, most of the particles, if if collisions, if they say that most collisions are not successful, it just means that those particles have energy above below activation. So these particles, or most particles, I can write here, right? So most particles have energy lower than activation, because in order to react they not only have to have the correct geometric orientation but also enough energy meaning energy must be higher or equal than activation. State and explain one way that the rate of reaction could be increased other than by increasing the temperature. um, Increase the concentration, and when you explain increase in concentration you have to say that, how when you explain it, yes, you have to say that more particles there are more particles per unit volume at high concentration, so you increase the frequency of collisions. Okay, you always have to refer back to the frequency of collisions or successful collisions. So we say increase, one way the rate of reaction can be increased: increase concentration of reactants, which means you would have more particles per unit volume. If you just say more particles, that's not accepted. You have to say that there is like more particles in the same volume, because if you just increase the number of particles, it doesn't mean that you increase the frequency of collisions, right? You have to really make them closer, so you have more particles per unit volume. And finally you say that so collision frequency increases. And also, if you just say collision number of collisions increases, that's also not accepted. We're very, very picky with the collisions because you have to refer to time. You could say number of collisions per second or per time unit, that's fine. But if you don't make reference to time, that's never accepted in any IB or A level, even in maybe only in GCSE, but I'm not sure. I teach my students to say collisions per second or something, or frequency. Give one reason why a reaction may be slow at room temperature. Well, room temperature is quite a low temperature, so probably activation energy is much higher than that. Yeah, so reactions are slow. So whenever they ask you why a reaction is feasible but slow, it's because it has high activation energy. High activation energy. Next question. Okay. How many three questions left, I think. Let's see if we can do it. It's how many pages? One, two, 2.5. Well, this is the last question. It's pretty. Oh no, three. Yeah. Well, I don't know. Should we finish or should we keep it till the next time? I'm just thinking. Okay, I'm thinking maybe let's do part three. Yeah, because I've been keeping you for what, for almost an hour. 50 minutes. Yeah, I think that's enough for today. Uh, but we don't have many things left. It's just we could finish it, but I feel like this 5 marker is pretty lengthy. And the titration one, there was this lengthy calculation question, which I think you're kind of cooked by now. So let's just do it next time. Yeah. So we'll have the part three, but I'll schedule it for a little later, because tomorrow, as I said, we have organic mechanisms for A level. Then I will explain on Friday structure 1.1 to 1.3, entire structure for IB students, SL and HL. And then I will schedule another one to finish this paper, but this would be hopefully like half an hour, not more than that. All right, so thank you for joining in. Again, if you want to get notifications about the lessons, you can subscribe. If you tell your friends about my channel, I'll be very happy. So, I'll let you go. Any questions, you can message me, and see you next time.